The last two videos of this unit will be about partial differential equations. Simply speaking, partial differential equations are differential equations, that is, equations that involve derivatives of functions, if the functions do not just depend on a single variable, but on multiple variables. Let's look at an example. Here I show you a partial differential equation that you get when you consider the movement of a quantum mechanical particle in one dimension. So this is the so-called Schrödinger equation in 1D. In this case, we have a wave function that is denoted as psi, which depends on two variables, namely, on the one hand, the time t, that describes the time evolution of the wave function, and the position x, which corresponds to the position space that the particle can be. And as you can see in this differential equation, we have a derivative with respect to t on one side and a derivative with respect to x, or actually a second order derivative with respect to x on the other side. So in this case, we have the essential ingredients of a partial differential equation, namely we have a function that depends on more than one variable, and also there are derivatives with respect to more than one variable. Now, as we will see, partial differential equations are not as uniform as ordinary differential equations, the differential equations of functions of one variable that we've been looking at so far. So they actually can be very varied, and first of all, simply because there's more freedom, because you have more variables, you can also have more combinations, but also in that the initial and boundary conditions can be very different. And I just show you here in this example. In this example, we can have an initial condition. And this initial condition is written here, which says, just an example, that at time t equals to 0, the wave function had a particular form. So this is just saying that at time t0, I start in a certain wave function. At the same time, when we, for example, consider so-called particle-in-a-box problems, and particle is confined to some finite region in space, we may also have so-called boundary conditions, namely that for all times t, the wave function at point 0 and L is equal to 0. So this corresponds to wave functions that are vanishing at the boundaries where they're confined. So this is a particular boundary condition in quantum mechanics. Now, what we see here is that in normal differential equations, we always had our initial conditions at some point in time. That's the value, and that's the value of the derivatives, and so on. Now it can be more varied. For example, here we have a combination of an initial condition and a boundary condition. Now, before we look at the second example, let's maybe briefly take one step back and just remind ourselves again about the properties of these partial derivatives that I write here. So you see I write it with this partial d, in this partial d notation that we have here. And essentially what it is that in essence they're just normal derivatives, but for a multivariable function. So it just means that ddt will act only on the variable t, and x will only act on the variable x. And in particular, the other variable is actually a constant for the other partial differential operator. So for example, when we look at ddx here, then t is actually a constant with respect to this operation, and vice versa. What this means in practice is that if we want to calculate, for example, ddx of t, then t is a constant for ddx, so this gives us a 0. Whereas, for example, dx t times x would give us simply t, because t is just like a number for ddx. So we just have the usual derivative relations that we need to do. So this is just to bring us all on the same page again. Now, to show you a second example, for example, that could be the Laplace equation. That is a common equation in electrodynamics, which looks like this. I have some function phi, which describes the electrostatic potential. And the equation is that the second order derivative with respect to x plus the second order derivative with respect to y equals to 0. In this case, for example, typically you wouldn't have any initial conditions, but you only have boundary conditions specifying what the value of the potential at a certain set of points is. So for example, that could be if we have some domain you could, for example, say, what is the value of phi of x, y on that boundary of that domain, and then solve the partial differential equation for the inside of the domain. As you can see, there's quite a bit of variation in the partial differential equations. And that is also part of the reason why there is no single nice theory for partial differential equations like there is for ordinary differential equations. So actually, in all of the cases that I showed you, these are still actually linear partial differential equations. For example, as you can see here, these derivatives, it's a second order derivative, but the derivative only enters linearly, or in the previous case, also here, this derivative enters linear, and this one enters linearly. But still, even for linear partial differential equations, there is no nice and comprehensive theory. So what we're going to do in this lecture is that we're only going to focus on one particular approach to solving a partial differential equation. And that approach is called separation of variables. And I'll explain it on the example of the 1D Schrödinger equation. Now, key to the separation of variables approach is the so-called separation ansatz, where we write down an ansatz for the desired solution psi of t of x. And what we write it is we write psi of t and x equals to f of t times phi of x. So we write it as a product of a function that only depends on t and one that only depends on x. And it's really important to be aware that this is a very restrictive ansatz. So this is absolutely not general. So this is really us just trying to find some solution to the problem. In the last video of the unit, I will then explain to you how we can go from this very specific restrictive ansatz to general solution. But let's focus now on this particular ansatz. We need to plug this ansatz into the equation. And when we do that, we get I h bar d f of t phi of x, the derivative with respect to t, equals to minus h bar squared divided by 2m, second order derivative of f of t phi of x, second order derivative with respect to x. And now, well, we were just talking before about how we have to read this partial derivative when we have both variables, t and x. And in the first case, what we know is that this derivative here only acts on f of t because phi of x is like a constant for d dt. So when we do that, we can simply take phi of x out of the brackets and we get I h bar f dot of t times phi of x. Now where here f dot I denote, of course, it's a shorthand for df dt, which, because f only depends on a single variable, coincides with the partial derivative. Okay, this was the left-hand side. Of course, we can do the same for the right-hand side. There, f of t is a constant with respect to d dx, so we can take it out again. And we arrive at minus h bar squared divided by 2m times f of t times phi double prime of x, where with the double prime I denote the second derivative with respect to x, as we did for the nth order linear differential equations. So what we've achieved so far is that we have reduced our partial derivatives to normal derivatives, but still in this equation, f and phi are still mixed together. So can we improve on that? And it turns out we can by applying a trick. What we're doing is we will divide this equation by f and phi in that way that we put f to the other side here and phi to the other side here, arriving at I h bar f dot of t divided by f of t equals minus h bar squared divided by 2m phi double prime of x divided by phi of x. You might ask if we're actually permitted to do this operation. because, you know, these functions f and phi, they could actually be zero. So can we actually divide by them? Now, in this whole derivation will not be completely rigorous in the mathematical sense. You can do that, but, you know, it's way too much work for what it's worth. And my answer to your objection would be, you know, this course is given by physicists. And, you know, as physicists, we're not afraid of dividing by zero. In essence, you know, things will work out even if the functions have a zero somewhere. Now, what did we achieve by doing what we just did? Well, we can make an observation, namely that the variable t now only enters on the left-hand side. And the variable x only enters on the right-hand side. So this is quite peculiar. What you see is that, you know, this equation holds for any value of t and x. So basically, now let's fix x and let's change t. You know, it's always the same value on the right-hand side, which means that this left-hand side has to be a constant. And vice versa. You know, if I fix t and I change x, I always get the same value, which also again means that the other side must be simply a constant. You know, in general, if you have that some function a of t equals b of x for all t and x, then these functions actually have to be constant. And we call that constant now lambda. And this is also what we're going to use here as our notation, so that, you know, knowing that the left-hand side equals a constant and the right-hand side equals a constant, and it actually has to be the same constant because left-hand side equals right-hand side, we arrive at two new differential equations, namely I h bar f dot of t equals to lambda times f of t. So I brought the f here again to the right-hand side. And additionally, we have minus h bar squared divided by 2m phi double prime of x equals lambda phi of x. And that's now nice because what we have here are just two ordinary differential equations. They just depend on a single variable. And actually, these are exactly the kind of differential equations that we solved previously. This separation into two normal differential equations, however, also comes with a price. Namely, we have this parameter lambda here. So in principle, we do not have just two normal differential equations, but they also depend on a parameter that in principle could take any value. Now, it turns out that once we take into account also the boundary conditions of the particular problem, the value of lambda will be restricted to certain values. And this is what we're going to look at next. So let's focus on the equation that deals with the position dependence. So this is the second derivative with respect to x of phi times minus h bar squared over 2m equals lambda times phi of x. For that, we need to apply the boundary conditions. So I said before, a particular set of boundary conditions is wave functions equals to 0 at 0 and L, so at x equals 0 and x equals L. So that directly translates into the boundary condition for this function phi here. Yeah. And what's now important to notice is that if I have these boundary conditions, when I change this parameter lambda that I have here, I cannot always have a solution, which is different from what we normally have when we have an ordinary differential equation with initial conditions. So saying that, you know, the value of phi at some point x0 is some value and the derivative at the same point is some value. So here we have boundary conditions which are at different points in space. There's actually an intuitive way to understand why there is not a solution for any arbitrary value of lambda. Now let's look at solutions that only fulfill the first boundary condition, so that the value of phi is 0 at 0. Now that leaves me to choose different derivatives of phi. So I can, you know, start here with different slopes. And with these initial conditions, I can solve this ordinary differential equation here uniquely. And what we'll find is that, when I start with different slopes, I get certain solutions, but they actually are not forced to ever hit 0 at L, which is the second boundary condition. Only for particular values of lambda, that is what happens, is that in this case, you can actually find solutions that go to 0 exactly at L. So by tuning lambda, we will find cases where we fulfill the second boundary conditions, whereas for most values of lambda, this will not be the case. Okay, so let's do this explicitly. To do that, we need to solve this differential equation that we have here. Of course, that's easy. That's actually just the example that we have been looking at in the previous video. So we know that when we rewrite the differential equation in that form here, then calling this here k squared, we know that the basis of solutions is phi 1 of x equals sine k of x, and phi 2 of x equals cosine of k of x. Now, I have two boundary conditions, as I said. So we have phi of 0 equals to 0. And that already tells me that the solution can only be the sine. So if I write the general solution as c1 times sine kx plus c2 times cosine kx, then from phi equals to 0 at 0, we know that the coefficient in front of the cosine must be 0. So this tells us that the phi of x must be some coefficient c1 times sine kx. Now we have the second boundary condition, and that is that phi of L equals to 0, which means that c1 times sine kl has to be 0. Now, this could be, of course, fulfilled by c1 equals to 0, but then we have a trivial solution which just says phi equals to 0 everywhere. So that's not interesting. So we need to figure out when the sine is equal to 0. And that sine is equal to 0 whenever k equals to n pi divided by L, and n equals 1, 2, and so on. I cannot choose n equals to 0 because that would again give me just a trivial solution 0. So whenever the argument of the sine is a multiple of pi, I get a 0. But you see that actually gives us a condition on k that it can only take discrete values. And that immediately translates now to the values that lambda can take, namely that we have 2m lambda divided by h bar squared equals to k squared, as I defined it up here. So it's n squared pi squared divided by L squared. And thus we arrive at lambda n equals to n squared pi squared h bar squared divided by 2m L squared. So here we find now that lambda can only take discrete values, and we call these the eigenvalues of this differential equation. In quantum mechanics, we'll actually see that these eigenvalues correspond to the energies of the solutions. So what we have seen now is that the boundary condition gave rise to this discreteness of the allowed values of lambda. So now for a given lambda that we determine now from the equation for phi, we now need to put that lambda, or these allowed values of lambda, back into the equation for f of t, and we get ih bar f dot equals lambda n times f, which again we have solved previously. So this gives us simply that f of t equals to some coefficient c prime times e to the minus I lambda n t divided by h bar. And with that, we can write down the complete solution, which was a product of f of t and phi of x. And we get the complete solution, which is psi of t of x equals to some coefficient, so the c prime times c1, which now I call c0, times e to the minus I lambda nt divided by h bar times sine n pi x divided by L. So I put in a value of k that I determined, n times pi divided by L. And that is a solution for n equals 1, 2, and so on. So we did find a solution of that partial differential equation. So these solve the partial differential equation. But still, as I told you before, these are only special solutions. How do we generalize that?